Okay, welcome to Carbohydrates. This is going to be a sweet chapter. So I did post a lecture that I made for organic chemistry, and it is essentially identical to the first part of biochemistry. So I'm just going to quickly go through, hopefully not give you whiplash, but to get the details, you'll want to watch that first lecture posted. And so we introduce you to carbohydrates, explain why they're different than amino acids and nucleic acids. And then lipids is the chapter that we'll talk about next. So you need to understand the Fisher projections and how they represent carbohydrates, the advantages of using the Fisher projection, and how every group that is horizontal is pointing out at you, and those that are vertical are pointing away. Be able to identify a D and L sugar by the very last carbon, or the very last chiral hydroxyl group there. It's off to the right, it's a D sugar. You need to be able to identify aldoses and ketoses, and then their general classification as if they were a pentose or a hexose or a triose or a heptose. That's simply the number of carbons found there. So like I mentioned, understand the difference between D and L sugars. Understand that has nothing to do with the way that they rotate plain polarized light, but these are chiral molecules, so they do rotate. But D and L simply refers to this configuration at the penultimate or last chiral center. So in order to draw an enantiomer of a sugar, all the groups are going to be on the opposite side. So you see D-allose and L-allose and D-glucose and L-glucose. It's not just the last chiral center. So if I wanted to draw L-glucose, I need to draw the complete enantiomer. Everything needs to be reflected across that mirror plane there. So listed in the study guide are the aldoses that you need to know. This is the family tree of D-grandpa glyceraldehyde and all his progeny. So you don't need to understand or don't need to memorize all these, but you can see that all of these are D sugars. So there's a whole nother family tree for the L sugars, which would just be the mirror images of these, and they would extend down from L-glyceraldehyde. But since nature prefers to use the D sugars, those are the ones that we will focus on. So there's actually 16 possible stereoisomers. Again, this is only showing 8 for the hexoses because there's a whole nother 8 for the L sugars. Ketoses, we have a few less stereocenters, so we've got a few less possible stereoisomers. And again, in the study guide, it will let you know which of these you should memorize. Now, a very important skill is to be able to draw these in their cyclic form. And so in a 5-membered ring, those are referred to as furanoses. In a 6-membered ring, those are referred to as pyranoses. And understand how to go from a Fisher projection into these furanoses or pyranoses. So again, in the previous lecture, I spent a lot of time in how to orient these hydroxyl groups. But essentially, those off to the right are found down. Those off to the left are found up. And then you close with, most frequently, the penultimate hydroxyl group, especially for hexoses. And so this one needs to go into the plane so it can attach the carbonyl. Notice when this goes into the plane to attach the carbonyl to make the hemiacetal, that pops this CH2OH group up on top there. That leads to 2 anomers, so the alpha anomer and the beta anomer. The actual anomer that we have here, how we determine if it's alpha or beta, actually depends on that configuration at that last chiral center there. So if this is a D sugar and this is up, that is referred to as a beta anomer. So here's the process. You take your Fisher projection, you lay it down, you wrap it around, and notice that this is a D sugar. So when it comes up into the plane, so it can attach that carbonyl, it pops the CH2OH. So if you're closing up with that last chiral center and that CH2OH goes up, then you know that it's a D sugar. And so when you attack that carbonyl, you can attack from either the top or the bottom. And again, the configuration here, if it's an alpha or a beta, actually depends if this is a D sugar. If this was an L sugar, that CH2OH would be down. And if that CH2OH was down, that would be an L sugar, and this would actually be a beta anomer there. So again, the anomer depends on the configuration of that last stereocenter there. So again, you should be able to draw these Haworth structures and be able to draw both anomers and be able to identify the anomeric carbon there. Now you can get 5-membered ring. These are known as the furanoses. And so in a furanose, same type of idea, you close them up. Now, in this case here, we actually closed up not into a furanose, but a pyranose, but we didn't close up with the last chiral center. This is a ketose sugar, so we actually closed up with this sugar. So notice off of this position here, there is no indicator if this is a D and L sugar. Actually, what we've got is this last sugar is pointed down, so we know that that's a D sugar. And notice that arrangement right there. That makes that the alpha anomer. Okay, so that should be a skill that you're familiar with. Now, which form it adopts actually depends on the type of sugar and the position of those OH groups. So actually, these open chain sugars are in equilibrium with their closed chain forms. Like I said, it really depends on the type of hydroxyl group there. And you can actually see down here the distribution. So we tend to get these pyranose forms. That is the most favorable in the beta anomer. You do get a little bit of the alpha anomer. You get the furanose form in the beta anomer and a little bit of the alpha anomer and even a little bit of the open chain form. So you don't need to worry about those numbers. You do need to understand that these can open and close, and in water they're in equilibrium. Now in a biological system, nature will find a way to make and wrap up the sugar into one of these preferred structures there. So the relationship between these two molecules here, where they just differ stereochemically, we would refer to them as diastereomers, but in carbohydrate chemistry, we refer to them as anomers, where they just differ at the anomeric carbon. So they still are referred to as diastereomers stereochemically, but the relationship is one of anomers. Now, if you had a pure cyclic sugar, let's just say I had alpha D glucose and I put it in water, alpha D glucose would open up and establish a new equilibrium between the alpha anomer and the beta anomer, as well as the open chain. And that is what's referred to as mutarotation. So this is an equilibrium process. And again, I could isolate pure alpha D glucose. And in our bodies, again, we have enzymes that will specifically make one form or the other, but just in an aqueous environment, these sugars will open and close and reestablish this equilibrium. And again, that process is called mutarotation. So, excuse me. Here's glucose. You can kind of see why we would maybe favor the beta anomer here. In this case, all of the OHs are in an equatorial position, which should be the most stable. But again, we get this equilibrium between both the alpha and the beta anomer and the open chain form. And there is ways to purify them. And that's because these are diastereomers, and diastereomers actually have different physical properties. So they have different solubilities and different melting points. Now, something interesting about glucose is it actually rotates light in the positive direction. And so it is what's referred to as a dextrorotatory sugar. So it rotates light to the right. And so glucose is known in medical settings as dextrose, the name dextrose coming from the way that it rotated plane polarized light. So like I said, in a medical setting, they wouldn't say, hey, let's administer glucose. They would say, let's administer dextrose. Now, something that is very important to understand is that D and L sugars and dextrorotatory and level rotatory and R and S are really independent ways of characterizing carbohydrates. So the way a molecule rotates plane polarized light really doesn't have anything to do if it's a D or L sugar or a D or L amino acid. And if it's R and S, like we talked about back in amino acids, that really doesn't translate to R and S or D and L either. So this dextrorotatory, level rotatory, plus minus, that is an experimental property. These terms DNL and RNS are just human-created ways of classifying molecules. And like I mentioned for beta glucose, you can see in this case here why it would be the favored form. And that's because all the hydroxyls are equatorial. Now that's not always true. In some cases, you actually see this anomeric hydroxyl group likes to be in the axial position. And that's referred to as the anomeric effect that we won't really talk about here in biochemistry. Another term that you should know is epimers. Epimers are sugars that differ at one position. So again, stereochemically, they're referred to as diastereomers, but in sugar chemistry, they're referred to as epimers. So you can see that mannose and glucose are epimers, and glucose and galactose are epimers. So in our body, we tend to do this epimerization, and we can quickly convert from one sugar to another just by switching the configuration at a chiral center there. So we don't have to synthesize all these sugars. You just switch one of them and you get the epimer. Those of you interested in organic chemistry, you can see how this can be done in organic solution through enolate chemistry. So again, in our bodies, we would use enzymes to do this. And you can also convert from aldoses to ketoses using enolate chemistry. So if you want to look at that, you can see this example here of how to convert from aldoses to ketoses. So we've got lots of isomeric forms of carbohydrates. You've got what are referred to as the constitutional isomers. They're constituted of the same atoms, they're just arranged differently. So examples of those are glyceraldehyde and dihydroxyacetone. Then you've got the class of stereoisomers. So again, we've got enantiomers that are mirror images of each other. And we can characterize those as being D or L. You got diastereomers here. So these are both D sugars, but they differ at one amino acid. So these are diastereomers, or not one amino acid, sorry, one hydroxyl group. And so these are also classified as epimers of each other. So D-ultrose and D-glucose are epimers of each other because, oh, actually I take that back, sorry. I'm getting ahead of myself. Here, they actually differ by 2 different ones. So these are just diastereomers there. So these are not mirror images. And so this would just be a plain old diastereomer. Epimers are where you just differ at 1 carbon. And so in this case, you differ at 1 carbon. So glucose and mannose are going to be epimers. They are still diastereomers. So all these, so epimers and anomers are diastereomers. Epimers differ at 1 stereocenter on the backbone. Anomers differ at the position at the anomeric carbon. They're still classified as diastereomers there. Okay, something else that we need to talk about is this idea of a reducing sugar. Okay, so hopefully you are familiar with the structure, how to draw the Haworth structure. And we need to talk a little bit about the reactivity of sugars. Now, we can classify sugars as reducing sugars, but this gets back into terminology that we used in Gen Chem, where things that are reducing actually end up getting oxidized. So reducing sugars by themselves get oxidized but cause the reduction of something else. So aldehydes can be oxidized to carboxylic acids, reaction you should be familiar with in organic chemistry. We used reagents like the Jones reagent to accomplish that. Now, carbohydrates can also be oxidized. Now, when they're in their hemiacetal form, they have a hard time being oxidized. But again, they can exist in equilibrium with their open chain form. And when they're in their open chain form, then you can actually take the aldehyde and that can lead to or get oxidized. Okay, sorry. There we go. Okay. So this aldehyde right here can get oxidized to a carboxylic acid. Since this molecule is getting oxidized, it is causing something else to be reduced. So sugars that can get oxidized are referred to as reducing sugars. I know it seems counterintuitive, but again, it's just like Gen Chem, where the thing that got oxidized was reduced, or sorry, the reducing agent. So reducing agents get oxidized and oxidizing agents get reduced. Now here's just an example. Again, this is not biologically significant because we don't have bromine floating around, but you can take a aldehyde, take some Br2 and water, and you will actually oxidize that aldehyde into a carboxylic acid. And when you oxidize one end of a sugar, it is referred to as an aldonic acid. And so you'll see these aldonic and other types of acids here. But again, the key is that in this hemiacetal form, you're in this equilibrium with the open chain, and then in the open chain form, that aldehyde can get oxidized to a carboxylic acid. So one of the reasons that they refer to these as reducing sugars is not because of what happens to the sugar, but what happens to the reagent that you're using to oxidize the sugar. And so one of these very common reagents is what's referred to as the Tollens reagent. And the Tollens reagent is a silver salt. So essentially it's an Ag plus here. And when you mix it with sugars that have an aldehyde, the silver Ag plus gains electrons and is reduced. So remember Leo the lion goes grr. So the silver gains electrons and is reduced and actually precipitates out as silver metal. So what happens is the sugar reduces the silver to silver metal. And when you do this in a glass container, that silver metal actually precipitates on the surface and makes a mirror. This is called the Tollens silver mirror test. Now what happens to the sugar, again, is it gets oxidized, but the process that it facilitates is a reduction of something else. So that's why they call them reducing sugars, because they reduce other things. Okay, so this is a test, again, not really biologically significant in our bodies because we're not going to have silver floating around. Just a little side note on reducing sugars. You might not expect a ketose to be a reducing sugar because you don't have an aldehyde at the end here that can get oxidized. But ketose sugars can undergo a isomerization using enolate chemistry. You get this enediol here, and that enediol can then be turned into an aldehyde that can then get oxidized. So ketoses can act as reducing sugars, they just tend to do so at a much slower rate. So you can actually distinguish between a ketose and an aldose by the rate in which it gets oxidized or causes something else to be reduced. Now, the reason I bring this up is because how they used to test if you had sugar in your urine, which is an indication of diabetes or some other disease, they would actually take Phthalate solution or Benedict solution, which are just solutions of copper 2+. Now, you may remember from Gen Chem that copper 2+ made a nice blue solution. And what they do is they would heat up these solutions of copper 2 ions in the presence of your urine. So some poor dude would sit down in or dudette would sit down in a laboratory and take urine and add these copper solutions and heat them up over a Bunsen burner. And if they turned red, that would indicate that there was sugar in the urine. And they could determine by how red it turned the amount of sugar in the urine. So this was one of the first tests for diabetes. And I just think it would be horrible down in probably a closed room, heating up test tubes of urine all day. But again, if it turned red, it indicated that there was sugar there. So again, these are reducing sugars, but like I said, fructose, which you look at originally, would not be a reducing sugar, but in the presence of the reagents that you use, which are very basic reagents, it can turn into a aldose sugar and then give you a positive test. It would just tend to be a slower reaction. So why we talk about this is we'll find out that sugars are still referred to as reducing sugars. And again, those are sugars that tend to be aldoses. Okay, so there's other ways to oxidize. You can oxidize at both ends of the sugar. These are referred to as alderic acids. And finally, you can just reduce at the bottom end of the sugar, and those are referred to as uronic acids. So you can see the options here. So essentially we got glucose, we oxidize at one end, those are called aldonic acids. You have the onic in the name. I can reduce at the other end, those are alduronic acids. They have the uronic in them. And then I can reduce at both ends, and those are referred to as alderic acids, and they have the eric in the name. You can also reduce. Now this happens in our bodies. Again, we're not going to use the same reagent here, but in the laboratory you can take sodium borohydride and reduce down the alcohols to sugar alcohols. These are non-nutritive, they taste sweet, and they tend to pass right through you. The problem is they also absorb a lot of water, and so if you eat too many sugar-free things, you can get a laxative effect from these. So sorbitol is actually used in X-Lax as a laxative now. Or it used to be phenolphthalein, which is the indicator that you may have used in Gen Chem. So interesting chemistry. But these sugar alcohols, again, on our tongue, they taste sweet, but they're non-nutritive. They don't have this handle for us to grab onto to metabolize them, so they just pass through. And so there's several different types of them, and they're known as alditols, and so they end with this ending of itol. So erythritol, mannitol, xylitol. This is included as an artificial sweetener. In fact, it's thought to inhibit bacteria growth. Okay, so in our bodies, like I said, we're not using sodium borohydride. We've got enzymes, and they can do some other modifications that kind of beyond the scope, but we just want to look at what happens. So here's a couple examples. This one right here should be very familiar. This is a deoxyribose. And again, this would happen enzymatically in your body, where you would remove a hydroxy group. This one right here, this is known as L-fucose. It's a sugar that you should know. It's found in your blood group antigens, and it's one of the few L sugars. And what's interesting is it also is lacking an OH out there. So it's lacking the OH on that terminal methyl group there. And anyway, interesting because it's also an L sugar. So some other things, you can replace hydroxy groups with amines. So we've got glucosamine right here that we'll see is very important later on. And we got galactosamine. So these are two very important amino sugars. And they're often acylated, meaning that they have this acyl group there. So they're in the amide formation. So there are various sugar modifications. In fact, here's some other modifications. These are the amino sugars that I just talked about. And like I said, they tend to be acylated. And anyway, yeah, just take a look at those and we'll talk more about them later. So you can have sugars decorated with carboxylates. You can have them decorated with amides and carboxylates. You can have them missing hydroxy groups. You could have them with just amino groups. And you can have them with phosphates. So all sorts of different modifications that you can actually make to sugars. So there's a significant variety. Here's actually another, these are known as the sialic acids. One of the most common ones is N-acetylneuramic acid. And it's derived from mannose-amine. So that lets you know that there's an amino sugar in there. And so it's got a pyruvic acid part. So this little group right here is pyruvic acid. And it is appended to a mannose that has been modified with an amine that's acylated. And then when you, anyway, what's interesting about this is you're not closing up with the last stereocenter here. This is a D sugar. But you're actually closing up with a center that is further away, this green oxygen right there. Now you notice that that green oxygen is off to the left. And so when you close up with it, this group goes down here. So this is one of the indications, or one of the problems with identifying an alpha anomer by looking at this group here, because this is a D sugar. And for D sugars, if this is down, that is the alpha anomer. So that is the rule that you can run with. If this is a D sugar and that's down, that is the alpha anomer. For hexoses, it's easy, but for the sialic acids, this is where that model of, oh, if the group here is down and this is down, then that is beta. Well, unfortunately, that doesn't work for sialic acids because this is a D sugar, that is down, and so that is an alpha anomer right there. So you need to kind of know if this is a D or L sugar. And what you can do is if it's a D sugar and the OH is down on the anomeric carbon, then it is alpha. And if the OH is up, then it's the beta anomer. And so this is on the anomeric carbon. So I always say in organic chemistry when I teach this that my rule that you can look at this group here works, except there are exceptions. So the better knowledge is what I just included down here. But if you close up with the very last stereocenter, that earlier model of looking at the position of this R group works. It's just in this case, the sialic acid, like I said, 99% of the time it works, but the sialic acids, it doesn't work because you're not closing up with that very last stereocenter. You notice you're actually closing up with one up here. Okay, so there are abbreviations. So those in the study guide that you should memorize, you should also know their abbreviations. You don't need to know all of these, but chemists get tired of saying full names, and so we like abbreviations and acronyms. And so you can see some of those there. Now, we talked about cyclizing sugars into their hemiacetal form. A hemiacetal has the form of a carbon, oxygen, carbon, oxygen H. And this is the anomeric carbon. This is a reversible reaction, so you can open and close that. But at hemiacetals, you can actually undergo a reaction where you can get a full acetal. So if you need a review, you may want to go back to your organic chemistry textbook and look back in the aldehyde and ketone chapter and look back into these hemiacetals. Now, there's a side note. I need to say that I'm referring to these all as hemiacetals. Our book actually refers to them as hemiacetals if they come from aldehydes, and hemiketals if they come from ketones. Now, there was a change a few years ago where everything was just referred to as hemiacetals, and they did away with the hemiketals. Now, for some reason, the nomenclature has swung back the other way. And so if you're reacting with a aldehyde, you're at hemiacetal or an acetal. If you're reacting with a ketone, then you're a hemiketal or a ketal. Now, I may find myself always saying hemiacetal because for the longest time, that was the approved term for both of these functional groups, whether they're derived from aldehydes or ketones. But just understand that now we're switching back. So when we say hemiacetal, this would actually be derived from a aldehyde, and an acetal would be derived from a aldehyde as well. But a acetal, again, has a carbon, oxygen, carbon, oxygen, carbon. It's like two ethers, but they're sharing a common carbon right there. And so, again, in organic chemistry, we refer to that as an acetal, or we may refer to it as the ketal, depending its origin. But in carbohydrate chemistry, we refer to that as a glycoside. So it still is this acetal functional group, but it's specifically referred to as a glycosidic linkage or a glycoside right there. So this right here is a hemiacetal. It's got the OH off of the anomeric carbon. If you don't have that H off of this oxygen and it's replaced with a carbon, that is now referred to as a glycoside. Now I'll show you the formation of a glycoside. Again, this would be in organic chemistry in a round bottom flask. In our bodies, using enzymes, the approach would be a little bit different. Same general idea. What we'd do is we need to convert this into a good leaving group. That leaving group is forced out by the neighboring electrons, and you get this oxocarbenium ion right there, so positive on the oxygen. And what you'd have is another alcohol come in and attack this carbon here, kicking those electrons onto the oxygen, and then you just do some deprotonation. The attack of this alcohol right here could be from the top or the bottom, which gives rise to the different anomers, the alpha or beta, but this is now referred to as a glycoside linkage. Now, this glycoside linkage doesn't have to be with just a small alcohol like ethanol, or in this example here, methanol. It can be with other alcohols that we'll see in just a second. So acetals are stable in base, so they don't react with Collins agents. And so this now is referred to as a non-reducing sugar. So if you have a glycosidic linkage, they're non-reducing. They're not going to open up into the open chain form and present an aldehyde that can be oxidized. So take-home message are these acetals or glycosides are not oxidized, so they're known as non-reducing sugars. So this is a non-reducing sugar because it doesn't have an OH at the anomeric carbon, and this is also a non-reducing sugar. We're going to just take a little side note. So there are other types of glycosides. Like I said, the examples that we saw were with OHs, but you can also have glycosidic linkages to nitrogens, and that should be very familiar to you because those are the structures of the nucleotides here. So we got phosphates on it, so they're nucleotides. And so these are what are referred to as N-glycoside bonds. Luckily, these don't open up in solution. They're stuck in that cyclic form. And again, these are non-reducing sugars. Okay, so that gets us through 8.1. So I know there's a couple different lectures there. Let me just kind of jump ahead and give you a preview of what we're going to talk about in 8.2. You can see the key concepts. But in key 2, or section 8.2, what we're going to do is talk about forming these glycosidic linkages with alcohols, which we just talked about, but the alcohols tend to be other carbohydrates. And we end up with a alpha glycosidic bond or a beta glycosidic bond, which we need to describe. But you notice here, we've got this form carbon, oxygen, carbon, oxygen, carbon, which is known as a acetal or a glycosidic linkage. And so if you notice over here, I now have a hemiacetal. So this can be opened up. So what we find out is this is the reducing end of a sugar because it can open up, present an aldehyde that can be oxidized. And this portion right here is now non-reducing. So these glycosidic bonds are non-reducing. Now, if we hook two sugars together, they're referred to as a disaccharide, composed of two monosaccharides. And so to characterize this, we need to understand which carbons are connecting and the orientation of this anomeric carbon right here. So this is referred to as a alpha 1,4 glycosidic linkage. Now the reason it's an alpha 1,4 is, well, let's figure out why it's position 1. So if we number around the carbon, you can see that that's carbon 1. Oh, let's get a different color there. There we go. So that's carbon 4. So I'm connecting carbon 1 with 4. So that makes sense. And then why is it an alpha linkage? Now I can't stress enough, the position here is fixed. So on the right-hand sugar, that position is fixed because that comes from the type of sugar. Now, the alpha glycosidic bond that's pointed there right here. This can be of one of two configurations, an alpha or a beta. Okay, that is variable. So in green, that bond is fixed because it's fixed by the type of sugar. The orange is variable. And so if we notice, that bond is of the alpha configuration. And so that is why we refer to this as an alpha 1,4 glycosidic bond. An alpha anomer connected from carbon 1 to carbon 4 of the next sugar, with a reducing end, because this position is actually a hemiacetal. So we'll pick up on disaccharides, jump into oligosaccharides or polysaccharides, and then we will finish up with glycoproteins. So I will do that in the next lecture, but hopefully you have these fundamentals down. Once you got these fundamentals of understanding how cyclic sugars form and how they can form glycosidic bonds, the rest of this tends to be fairly easy. And so we will talk to you then.